When we talk about attached objects, we're specifically talking about if those objects are attached by a rope and acceleration occurs, okay? So a few things that we can keep in mind if there's acceleration occurring with two objects that are attached by a rope. The magnitude of acceleration for each object is the same. So that makes sense, right? You have two objects attached by a rope. You pull one, the other one is going to follow along at the same acceleration. So that makes a lot of sense. The tension in the rope attaching the objects is the same. So the force of tension that the first object has, is going to be the same as the force of tension in the second object with the ropes that are attached to them. All right, they're attached to each other. And then the direction choice must correspond to actual movement and acceleration of the direction. So that's already something we are used to and that's happening a lot, okay? So it's really these first two that are so important for you to know. Obviously the third one's very important, but that's nothing new for you, okay? But all you need to know is that when I have two objects attached by a rope, I pull one of them, the other one's gonna go along with it, okay? So we're going to go over two specific types of attached objects and how you solve questions for these two specific things. So the first is Fletcher's Trolley. And so that's when we have a mass on a surface attached by a rope over a pulley to a hanging mass. So it looks something like this. Okay? So if I assume that this is a frictionless surface, then obviously it makes it a much easier question. So let's start with that. Let's start by assuming this is a frictionless surface. And then I want to figure out how I would determine the acceleration and force of tension in the rope. Because at this point, it's all going to be sort of mixed together. So it's going to be a little bit more difficult to find the tension and the acceleration. So I'm not even going to start with any numbers. I'm just going to show you how to set up the equations. Okay? So first step of force questions is always free body diagram. Here, I'm just going to draw it right on the diagram I've been given. So for the first mass, my force of tension in the rope is going to the right, because I'm assuming that's which way it's being pulled, right? Because obviously for mass 2, gravity is pulling it down this way. Okay, so that's what's going to happen. So our force of tension in the rope is going to the right. Then I have on this one, normal force going upwards and force of gravity. And I'm going to specifically say force of gravity for mass 1 going downwards. Okay, and then when I look at mass 2, that's the one that's actually pulling it downwards. So of course, force of gravity, and I'm going to say this is for mass 2, is going downwards. But force of tension is still kind of pulling it upwards a little bit, okay? So my force of tension is upwards here. So just remember that these two forces of tension are the same since they are being attached by the same rope. And the acceleration for 1 and 2 are also the same, okay? So that's really, really important to note. So what are we going to do? We're going to start by talking about each mass, okay? So I'm going to start by talking about mass 1. And specifically, I'm going to talk about mass 1 in the x direction because I don't really care about what's going on in the y direction for mass 1, to be completely honest. We know normal force is going to equal to force of gravity and for mass 1 because they're equal and opposite, which is pretty obvious there to us because it's not moving off of the table. And if we had friction, then we might care about the y direction because we'd probably need to find normal force, but we just don't here. So that's what I want you to do. I want you to treat kind of the two masses separately and do the sum of forces in one of the directions for each of the two masses and then see what kind of goes over. Okay? So for mass 1, I'm going to do the sum of the forces in the x direction, which should equal mass times acceleration in the x direction. I'm going to define right as positive because it is moving to the right. Okay? So what are my forces in the x direction here? It's just the force of tension. And that is equal to mass times, I'm just going to call this acceleration now instead of acceleration in the x direction. Because remember, for acceleration for 1 is the same as the acceleration for 2. One thing I should put though is mass 1 there because it is the first mass. And for all we know, mass 1 and 2 are different masses. Okay, okay, that's about all I can do, because if I'm trying to solve for force of tension or acceleration, I have both those there right now, so I can't actually do much. So I'm going to go over to mass 2 and see what we find there. So for mass 2, all I care about here is that y direction, obviously, because there is nothing happening in the x direction for mass 2. So this is a whole new situation for mass 2. We just know that there's two things, force of tension and acceleration, that can be the same in both, for both masses. Mass 2 is moving downwards, so I'm going to say that's positive. All right, then I'm going to sum my forces in the y direction for mass 2. So that's equal to mass 2 times acceleration in the y direction. Again, acceleration in the y direction for this one is the same as the acceleration in the x direction for mass 1, because they are moving together. Okay, so if downwards is positive, then my force of gravity for mass 2 is positive, and then I'm going to subtract the force of tension from that, should equal to mass 2 times the acceleration, which is the same acceleration as over here. So please keep that in mind. Same acceleration, same force of tension. Okay, so what is mass, or force of gravity for mass 2? That's mass 2 times gravitational acceleration. Now, the force of tension. Let's talk about this, because we don't know what that is, so we, again, have two unknowns. We don't know what force of tension is, we don't know what acceleration is, so I have to figure out what to do here. So, at this point, if I do want to solve for the acceleration, I have a nice equation over there specifically for the force of tension, and they're the same forces of tension. So what I can do is I can actually take this and plug it in there. You're thinking, why does that help me? Well, again, assume you have the masses, you just don't have the acceleration and you don't have force of tension. Well, what it does there, if I substitute M1A in for force of tension, look what I did. I got rid of force of tension. And our only unknown here is now acceleration. And sure, it's in two places, but I think I can still probably figure out how to solve for acceleration. We have done this before. So my first step is get everything with acceleration on one side of the equal sign and everything without it on the other. So I'm going to add M1A to each side, and I get M2A plus M1A. And then this is where I factor out A. Okay. And in the brackets, I'm left with M2 plus M1. Over here, I still have M2G. And then, what do? Well, to find acceleration, I can just divide both sides by M2 plus M1. So, that's what we're going to do, and we get acceleration equaling M2G all divided by M2 plus M1. And that's how you would find acceleration. So at that point, you could find your acceleration, the numerical value, and then you could go back to force of tension and know that force of tension is just mass 1 times acceleration, and then you'd use this equation to find force of tension. And so that's how a lot of these questions are going to look, where you're going to start with mass 1, go until you can't really break anything down anymore, and then you're probably going to solve for force of tension there. You're going to go over to the second mass. You're going to substitute what you found for force of tension in the first one in for this force of tension. You're going to solve for acceleration. You're going to go back to the original equation and solve for force of tension. Okay, so that's how we're going to do that. So let's do that with numbers now. Let's actually do that with numbers. And also, let's do that with friction, because let's face it, not having friction is just too nice. Just way too nice. Okay? So again, let's draw our free body diagrams. I am okay just drawing it on here. So I know my normal force goes upwards, my gravitational force for 1 goes downwards. Please make sure that you do decipher between mass 1 and mass 2, because in this case, we know that they are not the same. Okay, I know my force of tension is going to go this way, because that's which way the rope is pulling it, but then friction is going to oppose that motion, so my force of friction will be this way. Okay, so there's mass 1. Mass 2 is a lot easier. We know that force of tension is moving it upwards, but force of gravity will be larger downwards because this is likely going to be accelerating downwards. But again, just make sure that that is force of gravity of mass 2 because they are two different masses. So always differentiate between the different masses that you have. Okay, start with one of the masses. I'm going to start with mass 1. And I'm probably going to get an expression for force of tension in terms of the masses and coefficient of friction. Okay, that's what I want to do. So mass 1 is moving to the right because, of course, this guy, mass 2, is pulling it downwards. So mass 1 is going to move to the right. So I'm going to say right is positive. And some of my forces in the x direction should equal to mass times acceleration. Specifically mass 1 because we're working with mass 1. Okay. So what are my forces in the x direction? Force of tension is first, so I'll start with that. From that, I'm going to subtract my force of friction. Should equal to mass 1 times acceleration. Okay, we can break down one of these equations. Force of friction can be broken down into mu Fn, right? So let's do that. And now I'm stuck. So now I have 3 unknowns. I'm already expecting to have 2 unknowns because we're trying to determine acceleration and force of tension. And just like this previous one, I want to do this. I want to get an expression for force of tension in terms of what I have, masses and coefficients of frictions, but then with that acceleration still in there. And at this point, I don't have normal force. We are used to this at this point, right? So we know if I need normal force, I just need to go over to my y direction. So I'm going to quickly do that and say, oh yeah, I know sum of forces in the y direction is mass times acceleration, except for that's 0 because it's not moving off the table. So my normal force minus my gravitational force for mass 1 should equal 0, which means my normal force is equal to gravitational force for mass 1, which is mass 1 times g. Okay, we have that. So we can go ahead and plug that in for normal force right there. Okay, so we've been through that a few times now. Nothing new. So that's mu m1g. Remember, please label your m1s and m2s because you don't want to mess those up. So like I said, what you're going to be doing a lot of the time in these questions is getting an expression for force of tension. And so you can substitute it into the other breakdown once we earn Newton's second law for mass 2. Okay, so here I'm going to add mu m1g to both sides. And so there's my equation for force of tension. So I'm going to make sure that I just kind of know where that is because I'm going to go over to mass 2 now, and I want to make sure that I keep that in mind because I know I'm going to use it. Okay. Okay, mass 2, oh, so much easier because we only care about the one direction. So for mass 2, I'm going to go ahead and say downwards is positive because it is moving downwards. So it's really important that you have the direction of acceleration as positive. Okay, so my sum of forces in the y direction, well, force of gravity for 2 is downward, so I'm going to put that first because it's positive. And my force of tension, I'm going to subtract. That's equal to m2a. Okay, so already we know we can break force of gravity for 2 down into mass 2 times g. And we also know that I can substitute in my new expression for force of tension in here. Really, really important here. I'm going to subtract. I'm going to put this in brackets for right now, just because we tend to mess something up when we don't put this in brackets. So I'm going to say, okay, I completely replaced force of tension with what I found for it right there, okay? So I didn't change anything else. Well, I did. I changed FG2 to mass of 2 times gravitational acceleration. Why did I put that in brackets? Because so many people forget that if I'm subtracting everything in brackets, that subtraction applies to both of these terms. Okay, so I'm not just subtracting one of them, I'm subtracting both of them. So what does that mean? That actually means you're taking m2g, you're subtracting the first term, m1a, and you're subtracting mu m1g. Okay, so pretty much think about this as a -1 out front. Okay, that's what I want you to think of when you have that negative. Think of a -1 and multiply both of these things by -1. Okay, because if this also happened to be a minus, then it would turn into a plus. So it's just really, really important that you know that. Okay, and if you don't, then you'll end up adding something that you shouldn't, and then you'll get a wrong answer for all this hard work. That really sucks, to just get the wrong answer because of one minus sign. You don't want that. Okay, now, what the heck are we doing? We have this insane looking thing. We are solving for acceleration. Right, okay. So let's do that. So I want every term with acceleration in it on one side of the equal sign. So one there, that m1a has acceleration, this m2a has acceleration. So I'm moving that over. I'm going to add that m1a to the other side. So on this side, I'm left with m2g minus mu m1g. And here I'll have m2a plus m1a. Why did I do that? I did that so I can factor out an a, right? And what's left? m2 plus m1. Yay. Nothing on this side of the equation has changed, so I'm just going to rewrite it. Beautiful, and now I can divide both sides by m2 plus m1. So it gets a pretty big equation, but nevertheless we can find acceleration with it because we have both the masses, we have the coefficient of friction, we obviously have g because we always have g because it's a constant. So that's what you should get for acceleration for an equation, and let's plug in the numbers and figure out what that is. Okay. It's going to be fun. I'm going to run out of room completely. I thought I could fit it on one page, but we'll see. So mass of 2 was 4 kilograms. I'm going to have to write really small to fit all this in. 9.81 meters per second squared. And from that I'm going to subtract mu, which was 0.20, times m1, which is 2.5 kilograms, times g, 9.81 meters per second squared. I'm going to divide that all by m1 plus m2, which is 2.5 times, not times, what am I doing? Plus, oh boy, that could have really changed my answer too. Plus 4.0. Oh, I forgot to put kilograms in. Oh boy, okay, I'm going to try to squeeze acceleration in down here. What's my acceleration after we do all that? Again, when you're putting this in your calculator, please just do the numerator and then the denominator. So numerator, you should do bracket 4.0 times 9.81 and the bracket, minus bracket 0.2 times 2.5 times 9.81 and the bracket, press enter. Then do that divided by bracket 2.5 plus 4.0 and the bracket. And you should get 5.3 meters per second squared. Oh, that's squishy. That's real squishy there. But there's your acceleration. We got it. Okay, doesn't that sound like fun? We're not even done the question. We had to find acceleration, which we did. Yay. And force of tension. Okay. But the good news is we have this nice little equation for force of tension right here. Okay, I'm not going to try to squeeze this in here. It really is just a big old mess. So let's take that and write that on this next blank page. So remember, force of tension was m1a plus mu m1g. So I found that when I was looking for stuff for my first mass. And now I have that because I have my acceleration, right? I have that 5.3. So really all I have to do now is plug in that 5.3 for acceleration. So it does make life a little bit easier once you find that. So getting the acceleration is the really tough part. And then once you have that, getting the force of tension is nice and easy because you've already done the work of finding an equation for it. Okay. So this is what we should be plugging in for that. And we get a lovely force of tension of 18 newtons. Remember not to actually use 5.3, use your previous answer, or to at least, 5-6 decimal points. And there we go. Doesn't this look like so much fun? Come on. You can figure that out. I mean, there's a lot of places for little mistakes and errors and stuff here and there, but don't worry. I believe in you guys. Okay, I have one more example for you with Fletchers Trolley, and then in the next video we'll do Atwood's pulley because, yeah, it's too much to do all in one video. It's just too much. Doesn't this look fun? So here you go, you guys. I'm basically throwing everything difficult that I can throw at you. Well, actually, I'm not. Because what didn't I give you? There's no mu. There's no coefficient of friction. So I actually did make this a teensy bit easier on you than I could have. I could have also thrown in friction in here and be real fun. But I'm not going to do that. Okay, so we're going to assume that this is a nice frictionless surface for mass 1. And that does make life a lot easier. Okay? So start by drawing your free body diagrams. At this point I am going to kind of draw a different one for mass 1 because it's just feel like I don't have enough room there. So here's my mass 1. It's kind of on this incline like that. Okay, so for mass 1, what do we have? So we have the force of tension kind of going this way because that's how the rope is. Okay. But we're always assuming that the hanging mass is pulling the mass on the surface down, okay? Well, actually, in this case, up. So we're always assuming that it's basically going to go in the way of the force of gravity, right? Gravity is usually the strongest force of all of these. So my force of tension is going up the incline, but I don't have friction in this case. So I'm assuming that there's no friction. So that makes life kind of nice for us, so I don't have to put friction in the other direction. However, I know I do have a normal force going that way, and I know my force of gravity is not perpendicular to the normal force, it's straight down, which means I have to break this into x and y. Okay, so there's my y direction, or perpendicular to the incline. There's my x direction, which is parallel. So the force of gravity for 1 in the y direction, force of gravity for 1 in the x direction. Oh my goodness, doesn't that look fun? And then we know that if this angle is 15, then this angle right here is also 15. Sorry, that ended up being a bit of a mess, but hopefully you guys kind of get it. We have drawn this triangle. I can't believe that's a word I forgot. We have drawn this triangle quite a few times at this point. I'm going to just draw my free body diagram for mass 2 right on the diagram because my force of gravity for 2 is going downwards and my force of tension is going up. This is going to be fun. Okay, well, again, sometimes you have no idea what you're going to do, but you're just going to go through the motions. So we know we're determining acceleration and force of tension. So I'm probably going to have to find an expression for force of tension for mass 1, and then go over to mass 2 and solve for acceleration, and then go back to mass 1 and find force of tension, right? So it sounds easy. It's just in practice not as easy. But take it one step at a time. So mass 1, let's start with that guy. Oh, this looks fun. Okay, so here's the thing though. There's no friction. So I probably don't care about the y direction. So let's just start with the x direction. Let's be positive and think positive and be like, I want to see if I don't have to use that normal force and force gravity in the y direction. Okay, so I'm just going to say up the incline is positive because mass 1 is going up the incline. And I'm just going to set up Newton's second law in the x direction for mass 1. Oh, I always forget the mass number there. Please, please don't forget that. Okay, so what are my forces in the x direction? So, well, I have force of tension moving up the incline. But then, of course, I have another force. What is it going down the incline? That's the force of gravity for mass 1 in the x direction. Don't you just love force subscripts? It gets insane sometimes. Okay, so that's equal to mass 1 times acceleration. So what can I do here? I know force of gravity for 1 in the x direction. Well, force of gravity is m1 times g. X direction, it's on the opposite side of the triangle, so that is going to be times sine of the angle equals m1a. Okay, so force of tension, I can get an expression pretty easily here. I just add the m1g sine theta equals m1a to both sides. I get m1a plus m1g sine theta. Okay, fun. So there's my force of tension, or at least my equation for it. So I'm going to make note of that. And now I'm going to go on to the other page and start Newton's second law for the second mass, okay? So let's do that over here, or else I'm going to lose my mind. Okay, so remember for this one, we had force of tension going upwards and force of gravity going downwards. And downwards should be positive because that's the way it's moving, okay? So when I sum my forces in the y direction, it's equal to mass 2 times acceleration. Okay, so again, my forces. Force of gravity for mass 2 was positive, and force of tension was negative because it was upwards, okay? And that should equal to mass 2 times A. Okay, so force of gravity for mass 2 is just m2g, so it's back nice to having like no angles or anything like that, because this is just purely up and down, okay? So that's really nice. Now my force of tension, I have to subtract my force of tension here. So I'm subtracting this whole term right here. So please remember, you're subtracting both the m1a and the m1g sine theta. So I'm going to subtract both of these. G sine theta. That's what it was, right? Yeah, it is. And that should equal to mass 2 times the acceleration. Okay. Get everything with acceleration on one side of the equal sign. So m1a and m2a, I'm going to add the m1a to both sides. So m1g minus m1g sine theta left over here. So you get m2a plus m1a. See how it's starting to get a little bit repetitive? Like, honestly, once you get to this point, be really, really careful when you're setting this up. Right, when you're setting this up, like, be so careful with that. After this, it really does start to get repetitive, and you will get it within doing it a few times. Like, you really will. After this, it's just a lot of busy work, but we've done it a million times. Well, maybe you haven't. I have, and you will get to that point if you practice, right? And that is the whole point of physics. It's just like math. It's just like studying for math. Like, you have to just do a ton of practice. Okay? All right, I'm going to plug this in. What was my two masses were, M2 was 4 kilograms, M1 is 2.5 kilograms again, and my angle is 15 degrees. So, we got M2 was 4 kilograms times G minus mass 1 was 2.5 times G times sine of theta, and the angle was 15 degrees, divided by 4.0 plus 2.5, and that whole acceleration is then equal to 5.1. Okay. Again, make sure your calculator skills are okay. I would recommend putting that into your calculator just to make sure that you get 5.1 as well, because you would hate to do all that correctly and then not get the right answer just because of that. And then we go back and find our force of tension. Okay, and we're already solved for it. So M1A, which is 2.5 kilograms. The acceleration we got was 5.1. Please use your previous answer. Then M1G sine theta, so M1 again 2.5 times 9.81 times sine of 15. Okay, and then we get a force of tension of 19 newtons. Whew. Okay, so it actually, in my opinion, it's just as bad as this one. Actually, in a way, it's kind of easier, because at this point, hopefully, we're really used to this stupid triangle and know that the x direction, force of gravity in the x direction, is always just mg sine theta. In the y direction, it's always mg cosine theta. So I actually think this one's better than the previous one. the way I could really, really make your life crap with this is if I then added friction to this. And yeah, I could do that. I'm pretty evil. But at this point, I just want to make sure you know how to do the stuff with friction if it's on a level plane, okay, like this. Know how to do this without friction. And then you'll be able to put it together with friction in them both. Yeah, so good luck with practicing on those ones, okay? So I would definitely do some practice before you move on to Atwood's pulley. It's still attached objects and the same basic kind of theory that we're going to use, but just, yeah, no. Go work on this for a bit. Okay.